If you combine the power of deep learning with the expressiveness of graph-structured data, you will explore a whole new world of possibilities. Welcome back to the final installment of the Applied Deep Learning course 2021. Today we're going to talk about graph neural networks, and super exciting research topic. Before we get to that, as always, please head over to Tool now and take a few minutes to see if you can remember what we talked about in the last lecture. Last week we talked about explainable artificial intelligence, and we learned a couple of terms related to that. What do we mean by interpretability and explainability? Interpretability is the passive characteristic of the degree by which humans can understand a cause of a decision. On contrast to that, explainability is the active characteristic of a model taking action to clarify the internal functions and more specifically the output that it produced to us. So one thing of how easy it is for us to understand, and the other thing is how easy it is for the network to explain itself. How can you achieve explainable artificial intelligence? There are a couple of ways here, but broadly you can categorize them into transparent models, where the model itself has an inherent structure that can be understood, or by using post hoc methods that analyze kind of a black box model and try to understand a model without actually looking into every single operation that happens inside. How can you get some explanations for convolutional neural networks? Well, there is one quite simple method. You can just visualize the gradients by using saliency maps, or if you want, you can also use some more advanced techniques that we talked about last time, like LIME or RISE, where you kind of tweak the input a little bit and then see what happens in the output. And by cleverly constructing modifications in the input, we can kind of try to understand, okay, how does this change here reflect our output? So if we kind of blank out some parts of the input, will we still get the same prediction? And if no, that part of our input apparently was responsible for a certain prediction. How do we get explanations when we perform reinforcement learning? In that scenario, we can, for example, replace LSTMs or gated recurrent units with a simple state machine using quantized bottleneck insertion. And last but not least, how do we get explanations for generative adversarial networks? Here we saw one really interesting and one cool idea is that we can combine the generation of images with the instance segmentation, and we can identify then neurons that correlate to specific concepts. And by activating or deactivating these neurons, once we've identified them and say, okay, this neuron kind of makes trees somewhere in the image or generates trees in the image, and this neuron generates, I don't know, doors, we can specifically create images that have certain characteristics at certain positions in the image. Now to today's topic, graph neural networks. So far, when you look back at what we had in our course, we talked about images, time series, or other sequential data. And we typically processed it either in a feed-forward neural network or even some recurrent neural networks. But what happens if our input data itself, the data we're trying to reason on, is graph-like? When you think about it, many problems in the real world can be formulated as graphs. One example would be a molecular structure of a chemical compound, where you have certain atoms and they have bondings between them, and this understanding of how the molecule works like, or how the chemical compound looks like, is a structure on itself. Another example would be a street map. If we have a street layout, we have intersections and roads, you can represent this very well with the graph-like data structure, where, for example, the intersections are nodes and the roads are edges between those intersections. Finally, we can use some recommendation or social network scenarios where you have people knowing other people, and then if you want to get some recommendation based on some previous knowledge, you will kind of try to reason on this graph-like data structure that you have. So what are graph neural networks and why are they so powerful and so exciting? The main idea that we have for graph neural networks is very similar to what we have for many other fields. The idea is we take our input, in our case now it is a graph already. We try to learn a representation, a better representation that is specific to our problem, that helps us to reason on our data, on this problem. So we take this input graph here that is represented by the nodes X and the adjacency matrix A. We transform this graph into another graph. This is the learning part of graph neural networks, where we have some latent representations of the nodes with kind of more information on each node. And then we try to do something meaningful. We try to reason on this graph, on this learned graph in this latent representation. And at this point, you will probably have at least 3 questions. First question, what is this something that you can do once you have this graph? The second question, where do I get my input graph from? What does this thing look like? And of course, the most important question, what is this whole GNN box here doing? How are we getting a suitable representation or a more expressive representation of our input graph? And I would like to start with the first question, what is the things you can do with such a graph? Assuming we have been able to come up with a latent representation of our graph that is able to represent our problem better, what can we do with it? And the first thing we could do with it is we could try to answer questions about a specific node. That thing would be called node classification. And one example of node classification could be if you have a data set of research papers and the edges between those nodes would be citations, then you could say, okay, I have a certain paper. Which research subject is this paper all about? And you could try to kind of infer information about one specific node. You want to ask, is this node important? Is this node something, has it certain features? And all of these questions would be node classification, fall under the category of node classification. Another thing that we could do with this learned representation would be that we could try to answer questions about the entire graph structure. This would be called graph classification. So we take all nodes and everything we've learned into consideration and try to aggregate this into one statement or one answer that we're trying to get about the entire graph. One example where this could be meaningful is if you talk about chemical compounds and certain properties of them. You could try to ask the question, this chemical compound, does it have a certain property? Does it, for example, inhibit certain bacteria? Therefore, it would have some antibiotic effect. And this is something that we will see also later. This would be called graph classification. The next thing we could do, and the third and last one, is link classification. Obviously, we had questions about nodes, we had questions about the entire graph, but we can also ask questions about individual connections between 2 nodes. In this case, we have this node H, and we would like to understand some of the properties, how it connects to some other node. One example where this could be useful is if you have, for example, a database or a graph with products and people, you could try to answer the question, which product will that person buy next? Which would be a link between two nodes in this graph. You could also even try to say, okay, I'm kind of starting with a dense graph, and then I'm trying to understand which nodes are relevant and which ones are not relevant, and then do some classification on this end. The second question that we have is, where do we get this input graph from that we're using for graph neural networks? Well, the answer is, it's a modeling decision, and it's our responsibility to come up with a suitable representation of our problem that is in a kind of graph-like formulation. It can be that there is not one unique way how we can represent our problem in a graph, but often the structure of this graph is given by the underlying problem. Coming back to these chemical compounds, you have molecules being the nodes, and the bonds between them would be the edges with certain properties, or a street layout. If you say the intersections are nodes and the roads are edges. In this case, we would also have the structure kind of naturally evolving how we form our input data. One thing I would like to mention here is that information is typically attached to the nodes, and not just in an arbitrary form, but in a so-called distributed vector representation. So let's talk about these nodes. Typically, nodes are represented by certain features about these nodes. Nodes are not flying around somewhere, but we know a certain set of information about each node, and those would be the features. And we can, like, say, have 10 features for each node. Then we would have this r to the power of 10 here, and we can stack all of those features for all of our n nodes to get this capital X, which would be the feature matrix of our entire graph. Notice one thing, if we just stack them, we actually already define a certain order. So we have to make sure that whatever we do afterwards with this capital X, it is invariant to permutations of our rows. So if we see like this node or that node first, it should not make a difference. Let's talk about this distributed representation. Here's a small sample here. What we have already seen sometimes before was this local representation, also called one-hot encoding, where you have your vocabulary size and whatever, and like one bit or one kind of flag in this vector signals that you have a certain class. For example, banana is the first one, mango the fourth one, etc. The problem that we have here is that there is no relationship between a banana and a mango. So if you compare them in this v-dimensional space, banana and mango wouldn't share any features. So it definitely makes sense to use a different representation which reflects similarity. And this is called a distributed representation. It usually is smaller. And how do we get this? Well, we've seen it many times before. Convolutional neural networks, for example, give us exactly those distributed representations as their outputs, like the last layer before we actually perform classification or regression. The edges, on the other side, can be represented typically as an adjacency matrix, capital A, where we have 1 in this matrix if there is an edge between the two, or 0 otherwise. Mathematically, we can then formulate our neighborhood of the node I by this Ni, where we say we include all of the features of all nodes, or we include all of the nodes here in this set that have an edge. And then if we want to operate on the features of all of our neighbors, we can define this multiset of features here, like we take the features of all nodes that a certain edge has a connection to. One thing to mention here briefly, What you've just seen, this definition of how we're arriving at our input graph, requires some human modeling decisions. Therefore, we might not be able to devise a very good initial graph structure. So we maybe have some shortcomings here, and it makes sense to maybe also revisit this at a later time to think about, does this representation really make sense for my problem, or is there maybe a better representation? And of course, this is an active field of research, as many other parts of graph neural networks. Similarly, this distributed vector representation that we've just talked about, this embedding, might also be suboptimal. If it's something that doesn't really reflect the information or the proximity of nodes to each other, it might be very difficult to work with that. Now that we know what we can do once we have this new representation of the graph, and we know how we get to our input graph that is the basis for all of our operations, there is one important question that needs to be answered. How do we get to this better representation? How do we learn a better graph? And luckily, there are three flavors how we can actually do this: convolutional, attentional, and with message passing. When you think back and think about what we talked about in this lecture, we started talking about neural networks and multi-layer perceptrons, where every node is connected to every other node of the next layer. You can also call it a dense or fully connected layer. And we discussed when we talked about images that these multi-layer perceptrons are not performing very well. And it makes sense that they're not performing very well because they neglect the inherent structural information that is given to us in images. You know, pixels that are nearby are obviously strongly correlated, whereas pixels that are far away are much less correlated. So everything, connecting everything with everything obviously doesn't make sense. So what we did back then is we came up with this idea of a convolutional operation. And these convolutional operations were now that we said, okay, instead of connecting everything in our input to everything in the next layer, we only take a look at a small patch. In our case, a convolutional operator, which is, as you can see here, a grid, like a 3x3 kernel, that we slide over our image to obtain the values for the next layer. Afterwards, once we had this done once, we performed this again and again, and with each layer we extracted higher level features that were more meaningful to solving our problem. And we can also observe here that we had some really nice properties with convolutional neural networks, because we get this local invariance that we basically slide the same kernel over the entire image, and we can detect features everywhere in the image. Doesn't matter if it's on the left top or right top, we can find them everywhere. And we leverage locality. Information that is nearby is processed together, whereas information that is far away is not directly being processed together. So we had some really nice properties with convolutional neural networks, and the question is, can we transfer this idea onto graphs? When you want to process something on a graph and you take this idea of, okay, I want to only look at a small part of my input image, what would the corresponding concept be in graphs? Well, we want to process information from our local neighborhood. We have a node and we want to process information from the neighborhood of that node. Meaning we can define a graph transformation function mathematically, f of x and a, by appropriately applying a local function g over all neighborhoods. So we have a function g that obviously should be a permutation invariant, so it doesn't matter if we read certain nodes first from the neighbors, it shouldn't matter. And we apply this operation g, this function, on each node, and on each node it kind of looks into the neighborhood and takes those features that it gets from the neighboring nodes into account to compute something else. And if we apply this to to all of our nodes, we can come up with a general recipe for graph neural networks. This function G, what is that? This is the secret sauce of graph neural networks and a highly active field of research. And now we're going to take a look at how such a G function then could look like. We had this convolution ideas for images, and I just said for graphs we want to have something very similar. So we want to take the information from the neighbors into account to update the node information. This is the same piece again, but in a more graphical way. So we have our node XB, and it is connected to 4 other nodes. And then we want to come up with a function G here that can take the node XB itself and the neighborhood, the features of the neighborhood of node B, and process them into another latent representation. The simplest way how such a function G could look like is by updating the node by multiplying it with its neighbors. So we're applying a function psi here on each node of our neighborhood, and then we have a fixed weight Cij that depends of course on the thing, and then we aggregate this information. What is this Cij? It's a fixed weight, and it usually depends directly on the adjacency matrix A. In the simplest case, it is the adjacency matrix. So we add up all the features of our neighborhood whenever there is an edge to them. This is useful for homophilous graphs where similar nodes are often linked together, and if you have very large graphs, because this operation scales very well. One thing that I should point out here is that the information we obtain from all nodes in our neighborhood here have to be aggregated somehow. This is this function here, this aggregation function that you can see, and then we apply like one final transformation, some nonlinearity phi onto the overall result. This is kind of a basic rule for convolutions for graphs. What we can do now is, if we have such a transformation, we can actually repeat this process a couple of times, meaning that if you think about like we have multiple layers before, here we can also repeat this same transformation a couple of times, t times in this case, and with each update step our receptive field would grow bigger, and initially you can only see information from your neighbors, but in the next step you can already have input from or receive information from the neighbors of your neighbors. T is usually a fixed small number of time steps, and as you might have guessed, another hyperparameter that is up to us to optimize for. To make this whole thing a bit more understandable, let's have a look at how such an update function would actually look like. If we assume that our graph is unweighted and undirected, meaning that Aij equals Aji, then we can aggregate information from all of our neighborhoods basically just through multiplying with the adjacency matrix. So we have our features H, we multiply them with the adjacency matrix A and with another weight matrix W, that is the learnable node-wise shared linear transformation. So this is the thing that we're actually learning here, this W, and a nonlinearity function sigma here, just to make this a bit more powerful. One thing that you should notice here, I'm not using A as it is, but instead A tilde. So instead of using the original adjacency matrix, we add the identity to our adjacency matrix to include the central node into this. If we wouldn't do this, we would only ever consider our neighbors, but not the information that is stored on our node itself. It's kind of a self-link, if you will. So this is important. If your graph doesn't have self-links, you would have to add this identity. Otherwise, you would lose the information that is currently stored in the node itself. You can reformulate this update rule per node, and then it would look like this. One problem that we have if we formulate it in such a simple way is that whenever you multiply with this adjacency matrix, the scale of the output increases. If you have 5 nodes or if you have 100 nodes in your neighborhood, you would get a different scale of your output. Therefore, we need some form of normalization. And one easy way of performing this normalization is by multiplying with the degree matrix of our adjacency matrix. So if we have 5 neighbors in our neighborhood, then we would divide by 5 to kind of keep the same scale in our output that we had in our input. And we end up with the first update rule called the mean pooling update rule. It's very simple but yet powerful and can already solve a lot of real-world issues. There is a slight variation of this rule that if we, instead of using this asymmetric multiplication here, if we replace it with a symmetric normalization, so from left and right with the square root of our matrix, we get the so-called graph convolutional network update rule. Node-wise, you can write it like this, and one thing that you should be able to see here is that now we're not only normalizing with nodes, like with the number of nodes we have on our current node, but also we're including the weight of the neighboring nodes. Enough talking, let's have a look at some code. Let's try to classify papers with graph neural networks on the CORA dataset. Before we jump into it, I just want to say a few words about the CORA dataset itself. The CORA dataset consists of 2,708 publications, so it's a dataset about research that is published, and published research typically has the tendency to cite other research. Again, this naturally looks like a graph, so you have influential papers that have a lot of citations, incoming citations, and then you have other papers that form like clusters where they're all citing each other. So in this dataset, 2,700 publications and around 5,000 links. We also have some features that describe each paper, where we have a dictionary of 1,433 unique words. And whenever that word, one of those words appears in that paper, then we would get a 1 there. Lastly, we have each publication in our dataset being classified as one of 7 categories of research fields, if you will, and this is exactly what we're now trying to do. The good thing about the CORA dataset is it's very small, and it has received kind of the title MNIST for graphs, because it has exactly like some super nice properties of being small and a very nice playground for various new algorithms in graph neural networks. So let's jump right into the code. Okay, I'm now in our Google Colab environment, and here is the code to perform exactly what I just said, that we want to try to get some information out of this CORA dataset. So I would start by installing some dependencies here, and I'm using TensorFlow for this example, as well as the Spektral library. The Spektral library is one of the frameworks that is very useful for graph neural networks, and specifically in this case, we'll use it to easily get the data set that we're interested in. So let's import them and let's have a look at our data set. In our data set, as we would expect, we now have 2,708 nodes with 1,433 features and 7 labels, because we have 7 different categories that each paper is classified into and that we want to predict now. So we can take from our CORA dataset, datasets can have multiple graphs. In this case, there's only one dataset, so I just grab this one. And now we can obtain the training masks, the validation masks and test masks, as well as the adjacency matrix, features, etc. that we're gonna need for the future here. Meaning, in this case, we're actually training just on 140 samples. We have 500 validation samples and 1,000 test samples. Let's have a look at some of our data. Let's have a look at paper ID 5. And these are the 7 classes that, that we have, one of these labels. And this thing here has a lot of zeros in our features, obviously, because there are only some keywords out of these 1000 that it actually has. Well, there was some one here, here's some one. So apparently this word appears in this paper. In order to create a graph convolutional network here, we need a couple of helper functions. And the first helper function here is a masked soft cross entropy and a masked accuracy. Why do we need this? Why can't we just use the cross entropy? Because this way allows us to actually only take the set of nodes that we're interested in. More specifically, the training set, the validation or the test set. So what we're defining here is we're taking the soft cross entropy loss on our logits, on the raw outputs and the labels that we get. And then we'd also take this mask that says which nodes are in our current set that we're looking at. And this is kind of a small trick that if we normalize it here, then we can actually just multiply it with the loss here and then reduce the mean, like just aggregate this, take the mean of our loss of all individual nodes to get the total softmax cross entropy loss. A similar thing we can do with the accuracy. We also take the logits and the labels. We pick the argmax and compare where they're the same. So we kind of check where the predictions are correct or not. And then we compute the accuracy by, again, taking the mean of it. But before we do that, we apply a mask here with the same trick that we only compute this accuracy for the masks that for the nodes where actually our mask tells us something. Now the graph neural network, the graph neural network layer where actually something would happen is defined by the following. We take our features, in our case the nodes are represented by their features, the adjacency matrix and a transformation matrix that is applied on the nodes themselves as well as an activation function. This thing here is the learnable function and this is a nonlinearity that we apply later. Then what will we do? We apply this transformation to our input. Then we get this transformed features. We multiply it with the adjacency matrix and apply our activation function. This is exactly what we've seen before. Training on our CORA dataset now could look the following. We take 2 layers. One would be a dense layer where we connect everything, so our inputs to this layer, and then we have with a certain number of units, and then we have a second layer that has 7 neurons as output because we want to arrive at 7 classifications of 7 different classes here. And we would then process our CORA graph neural network in such a way that we take our input features and the adjacency matrix, then apply the first dense layer. So we take the features, we run it through our first dense layer and apply a ReLo activation. So we arrive at some hidden features and then we would apply the second layer here, which is again hidden features with the adjacency matrix, but in this case we're only getting these 7 outputs, and given that our softmax cross entropy loss takes logits as input because it internally computes the softmax, we only need the identity function here. And this is the result that we get and we report the spec. Now we can do perform training with a standard training loop that you have already seen a couple of times, where we define an optimizer and we record the best accuracy, and for a certain number of epochs we record our gradient and then we run our features through our network. We get the logits, we can compute the loss according to our masks. In this case we are only interested in the training node, so we provide the training mask, and then for all of the watched variables we compute the gradient, apply the backprop step. And before we are done here, we can also run this again and have a look at our validation and test accuracy that we get here. So Basically, you can save the model here if it has better accuracy, but for now we're just writing this to the output. So let's run this and let's see what happens. In this example, we're having here 32 neurons, and we're training for up to 200 epochs. And what you can see is that training has completed with a learning rate of 0.01, and it kind of already got to some quite good validation accuracy here at around 75% after just 38 epochs. Afterwards, it didn't get any better. Just some sanity check that what we're doing here is actually meaningful is what happens if we replace our adjacency matrix just with the identity. I mean, what happened here is that we would change this into a standard multi-layer perceptron model where we have just the nodes themselves. So let's train this again, and what you will see is that the model will obviously not work as well because we're missing the information about which nodes are connected to which other nodes. We only have the features themselves. So if we're interested, this would be kind of the adjacency matrix. In our case, it would be this identity. And when we try to normalize the adjacency matrix, this would be the optimization that is being done for that we've seen before. We see that the results is slightly better, and this would be the improvement for this graph convolutional neural networks that we perform this normalization here. We can also try this, and we can see it's even performing a little bit better. And this is the standard procedure how you can train graph convolutional neural networks. Now that we've seen in great detail how graph convolutional neural networks work, let's take this and take one step up. The next flavor that we can have to build such a G function would be graph attention networks. So it's an extension where we're replacing those fixed weights, how we multiply our neighbors, with actual learned weights. So the features are aggregated now with this implicit weight that we learn here via an attention mechanism. And it's basically kind of this middle ground between the graph convolutional networks and the message passing that you will see in a second. And the edges here don't necessarily encode homophily. An example for this would be if you retweet a message, it doesn't mean that you agree with what the person said. So there is an edge between the two nodes, but it doesn't mean that it's a positive relation. So in these situations where we don't just encode node similarity, but some interactions between nodes, graph attention networks will provide viable alternative. As you can see, mathematically, what we're doing is we have this function alpha here that is also now depending on the xi and xj nodes themselves. So this is the learnable function, and it's already one step up from this graph convolutional networks. And if you're now saying, wait a second, attention, I've heard this quite recently before, then well, you're not alone, because we've talked about the attention mechanism quite in detail when we talked about transformers. And it turns out this is not a coincidence, because transformers in fact are a form of graph neural networks. If you have a fully connected graph and you use this attention mechanism, then a transformer is equal to exactly the thing that we're doing here. So you can view this attentional graph neural networks as a kind of generalization of transformers. When you think back how we use transformers to process sequential data, especially for natural language processing, is that we added these positional embeddings. Like we multiply our input to kind of keep this information of the order of our input alive. Without them, it's just a fully connected graph attention network. Now to the third and most sophisticated mechanism how this G function might look like. Because if you think back, we had an assumption so far that the connections were undirected and we didn't specify any of our edge features. And this is what we can solve with neural message passing. It's the most complicated and most advanced mechanism of these three. And what we're doing here is that instead of just multiplying with the features of our neighbors or with some weighted features, we're actually constructing messages that are being passed from one node to another. And these messages can then be conditioned on our edge features to incorporate this information. An update step would now look like the following. A node aggregates all the messages from its neighbors, and then using a permutation invariant function phi, it would aggregate all of them together to obtain the next time step. It's the most generic GNN layer, but it might have, as you can imagine here, some scalability issues or even some learnability issues, but it's ideal for chemistry or some simulations here because it can reflect information that is stored in the edges, which before that was not that easy. Let's visualize such a neural message passing step because I think it's still quite abstract. Imagine that we have two nodes XA and XD that are sending a message to our node XB. How would this go on? The nodes XA and XD are represented by their feature vectors. So it's the current state of these neighbors. And then we take a function here, this function psi, that incorporates the information from the node XA as well as XB. So they collaborate on creating this message MAB, and we do the same for the other nodes. So we have two messages, AB and DB. So these two messages then are being summarized by some function, for example, a sum or a mean. And once we have this, we take the current state of the node XB at a time step t-1. We process that together with the message, with the aggregated message that we've received from all of our neighbors, and then we arrive at the next node state. One thing I should mention here why this might have some scalability issues is because typically we have way more edges than we have nodes in our graph, or we can have at least more edges than nodes. And as you can see here, we will have to compute for each edge a certain operation here. Therefore, it is much more expensive to have a neural message passing graph neural network as in contrast to having a convolutional graph neural network. One final thing I would like to mention here is that this message passing thing here happens at the same time for all nodes. So what you're doing, you take the entire graph, you compute all the messages from all nodes to all neighboring nodes at the same time, and then the clock ticks. All of these messages are being aggregated and the nodes are updated, and that will be one time step. Now that we know the theory about graph neural networks, let's have a look at a few frameworks that can help us to bring this to some practical, meaningful applications. One framework that I would like to present here is pytorch-GEOmetric, which is a Python library for deep learning on irregular structures like graphs. It was originally developed by two PhD students at the TU Dortmund, and it has a couple of nice features like obviously the general graph data structure and processing of this, but also several methods from published papers, including the ones we've just seen with graph attentional networks or graph convolutional networks. And it's also highly optimized for performance by supporting multi-GPU and CUDA kernels as well as efficient mini-batch handling. Another framework that you can definitely use is the Deep Graph library. It's also a library for deep learning on graphs, and it's being developed by the distributed deep machine learning community. And as you can see here, it's an easy to use, so the framework provides an API that is used on top of other frameworks. So while the first framework was obviously tailored to PyTorch, the Deep Graph library can be used kind of on top of multiple frameworks, including PyTorch, TensorFlow, and MXNet. The next one is Spektral. It's another library for deep learning on graphs and was primarily developed and is maintained by Daniel Garatarola from the EPFL in Switzerland. It's based on the Keras API and TensorFlow 2. And what you can see here is that the choice of which of these libraries you're going to use probably depends on the underlying library that you use to train your models. It also implements many of these methods that we've just seen before, including graph convolutional networks or graph attention networks. Last but not least, GraphNet is a Python library for building graph networks in TensorFlow, and it was developed and is maintained by DeepMind by Google. And it's a flexible library to build various graph neural networks using 6 core functions. 3 of them are related to updating and 3 of them are aggregating. So you can also view all of these graph steps, this graph processing, by saying, okay, which functions operate on one node, one edge, or on some global attributes, and which functions are aggregating information from edge attributes, edges, or nodes. If you want to try out some of these algorithms on your own, you can go ahead and take some of these frameworks and pick some of the datasets that are already being published and readily waiting for you. If you want to browse through some of the datasets, including the CORA dataset that we've looked at before, you can go to this Relational dataset repository. They have a ton of datasets that you can use, as well as the Open Graph benchmark. It's a set and a collection of datasets, loaders, and evaluators, especially for graph machine learning. One thing I haven't talked so far is what are some of the real-world applications where these could be used, these graph neural networks, and potentially have already been used successfully. One example that is very interesting and was very hyped, so to speak, was graph neural networks for molecule classification. So what happened here is that scientists took graph neural networks and they tried to understand what properties certain chemical compounds have. So they used the graph neural network to classify whether a molecule inhibits certain bacteria or not. For example, Escherichia coli. And if it does, it is an antibiotic. So we can train on a curated data set of compounds where we know the response, where we know this has a certain effect on that bacteria. Once we've trained this model, we can try to apply it on a set of candidate molecules, and we take, say, the top 100 here and give them to some chemists to have a look at them and investigate them further. And this procedure actually led to the discovery that halicin is a strong antibiotic with a very unusual mechanism against bacterial strains that are resistant to many drugs. And it has made the headlines with AI helps to discover new antibiotics. But now that you know about this, you know how it came about and what's actually underlying here. The other example that we've already talked before is obviously transportation maps or street maps, where we want to try to predict the estimated time of arrival. And as we've talked before, you could say intersections are nodes and roads are our edges, or you could actually do something that has been done at DeepMind, which is also quite interesting, that instead of saying intersections are nodes and roads are edges, you reformulate the problem. And this is one of the things where we have to kind of put some brain power into it. So they kind of cut the roads into super segments. So the road are now the nodes, and these connected parts here are the edges. So these are connected here, and then you take some features like the road length, the current speed of cars going there currently, or some historical speeds, and then you can try to estimate the time of arrival from this. And they've shown to obtain extraordinarily good results with this, and I think it's being deployed. And when you use Google Maps nowadays, one of these graph neural networks is probably computing your estimated time of arrival. The last example I want to give is from a different field, which is automatic program analysis. If we are programming, then the computer programs themselves can also be formulated as graphs. I think most of us know this abstract syntax tree. It is a graph. And for example, we can say in our graph here, we have edges whenever a variable was written or whenever a variable was read. Then we construct an edge in our graph between those parts in our tree. And then, for example, we can use this to detect variable misuse, where potentially the program might crash if we run it there. Summing up, graph neural networks are particularly powerful because there are many problems in the real world that can be formulated or just come in the form of graphs. The graph neural network idea that drives this is that we take the input that is already a graph, learn a better representation that is more suitable to our problem, and then perform some reasoning on that learned graph, on that latent representation of the graph. We could either do node classification, where to try to answer some questions of specific nodes, graph classification, where we try to answer questions about the entire graph, or link classification if we want to know something about the interaction between two nodes. Graph neural networks come in three flavors: the convolutional graph neural networks that use fixed weights to multiply the features of the neighbors to compute the next update step; attentional graph neural networks, where you have a weighted, like a learned weight that helps you to kind of understand how the interaction between certain nodes are, instead of just multiplying the features with each other. And then you have the most sophisticated way of performing graph neural networks, which is message passing, where you compute messages from each node, from each kind of connection. You can incorporate additional features from the edges, and then you summarize it to update the node for the next time step. And there are various libraries and datasets that are already available and that you can use to solve your problems in the future.